Topic is vector spaces, which is sections 2.8 slash 2.9 in Lay's textbook, 4.1 slash 4.2 in Edwards. What is a vector space? Vector space is a non-empty collection of objects given two operations, namely addition operation and scalar multiplication. If those objects satisfy 10 axioms or propositions, then we say that that set, let's call it V, under these two operations, namely addition and scalar multiplication, form a vector space. The notation plus with a circle and a dot with a circle around it, those are like abstract addition and abstract multiplication. Sometimes the operations are ordinary addition and multiplication, sometimes are abstract, which we'll talk about that in a few minutes. But first, let's go over the conditions in which a set of objects form a vector space. Those conditions are known as axioms or propositions, and they are as follows. If you select any two elements in the set, add them up, and the sum is still a member of the set, then we say we have satisfied the axiom closure under operation addition. If you select the element in the set and multiply by a scalar, and the result is still an element of the set, then we have satisfied closure under scalar multiplication. If the order of how you add two elements in the set doesn't matter, then this is commutative. So this is one of the conditions out of 10 has to also satisfy. If you grouped three elements in the set, in order to add them, you regroup them, and the answer is still the same. That's called associativity. That's like regrouping addition. There is this element called zero vector. Does not have to be the zero, but the meaning of the zero vector is like, what do I add to any given element in the set to get the element back? Sometimes the zero vector is zero, sometimes it's something else. It all depends how the addition and what scalar multiplication is defined. On the other hand, if you have a zero vector, then you are guaranteed to have something called additive inverse. Additive inverse is like when you select any element in the set, what do you add it with in order to get the zero element or zero vector back, which you got it in axiom number 5. So additive inverse solely depends on what? Zero vector. If zero vector doesn't exist, additive inverse doesn't exist. Then we have these distribution law of addition. So this is like if you distribute or multiply a scalar by sum of the two elements, you get this, just like algebra classes. Distribution law for scalar addition, a and b are scalars, you multiply it by u, so you get a times u plus b times u. Associativity law for multiplication by scalars, that's ab times u, you can write this as a times b times u. And finally, 1 times any element is the element itself, and this is called identity axioms. So the bottom line is, in order to prove a set given two operations, namely addition and scalar multiplication, forms a vector space, we have to satisfy the following 10 conditions or axioms. So with that in mind, let's see if we can kind of go over a couple of examples. So keep in mind, positive is ordinary addition, dot is ordinary multiplication, but a plus with a circle is abstract, and a dot with a circle is abstract multiplication. For example, let's say you have set of real numbers. In ordinary addition and multiplication, 3 plus 7 is 10, and 3 times 7 is 21. However, if I define my addition as x plus y is equal to y minus x, and c times x is x to the power of c, so 3 plus 7 is no longer 10, is according to my definition of operation, addition operation is 4, because that's how it's defined. And 3 times 7 is not 21, is 7 to the power of 3. Excuse me. So it all depends how you define addition operation and what? Multiplication by scalar. Let's do this problem. Suppose set S is set of all real numbers with ordinary addition and ordinary scalar multiplication. So it's not abstract operations. How would you prove what? This set forms a vector space. To begin with, you define your variables. You go let x, y, z be what? Real numbers. And a, b, c are constants. Now the question is, when you add two real numbers, do you get a real number? Yes, so closure under addition is satisfied. When you multiply, let's say what? Any real number by, say what? Scalar, let's say c, would that be still a real number? Yes, it is. So therefore, closure under scalar multiplication is satisfied. Does the order of how I add two real numbers matter? No, it doesn't. Does it matter how I regroup what? Three real numbers when I add? No, it doesn't. Associativity. What is the zero vector? What do I add to a real number to get the real number back? Well, turns out the zero vector is 0, the number here. Okay. And following the remaining axioms, now the question is, what would be the additive inverse? Well, additive inverse would be like, what do I add to any real number to get the 0? Well, turns out it's negative x. So negative x is the additive inverse. And then you can follow the remaining axioms, and lo and behold, all the 10 axioms are satisfied. Remember, to prove a set under given two operations, namely addition and scalar multiplication, forms a vector space, every single axioms out of 10 has to satisfy. If any of them fails to satisfy, then that set does not form a vector space. Since all the axioms are satisfied, so we say the set of all real numbers under ordinary addition and scalar multiplication operations form a vector space. But keep in mind, not all the set of objects under given operations, namely addition and scalar multiplication, form a vector space. So let's see some counterexamples. Suppose S represents set of all rational numbers. You know what rational number is. That would be the ratio of two integers where b is not equal to 0. Otherwise, this would be undefined. However, axiom number 2 fails, because if your scalar is the square root of 2, which is irrational number, you multiply that by a rational number, the result is no longer a rational number, it's a rational number. So because axiom number 2 fails, so the set of all rational numbers under ordinary addition and ordinary scalar multiplication do not form a vector space. So this set does not form a vector space because axiom number 2, which is a scalar multiplication, failed. The next problem is set of solutions, set of all solutions to this first order non-homogeneous linear differential equation, namely y prime plus 9y is equal to 4x squared. So what you do in order to disprove that this guy is does not form a vector space, so you say, okay, let y1 and y2 be solutions of this what? Differential equation. In other words, let y1 and y2 be a member of the set S. Because they're the solutions, therefore what? They have to satisfy the given differential equations. However, axiom number 1 is the sum of these solutions is also a solution. When you replace these y's here with y1 plus y2, go through the manipulation. At the end of the day, you're going to get 4x squared plus 4x squared, which is what? 8x squared, which is not the same as what we had, which was 4x squared, because we ended up with 8x squared. So therefore, y1 plus y2 is not a solution of this differential equation. In other words, axiom number 1 failed. Therefore, what? The set of all solutions to this differential equation does not form a vector space. Thank you.